The next thing we want to talk about over the next 20 minutes or so would be some interpretations of the standard deviation. Standard deviation, or whatever measure of spread we're looking at, is very, very, very important. Spread is a huge concept in data. So we're going to talk a little more about how to interpret these things. And so the first rule we have is the range rule of thumb. And basically, we're going to find that about 95% of our data falls within two standard deviations of the mean. Okay, so we could pretty much estimate the minimum and maximum values if we know the standard deviation and the mean. And so we estimate the minimum value of our set to be x bar, the sample mean, or it could be the population mean if that's what we're looking at, minus 2 times the standard deviation. And we estimate the maximum to be x times the standard deviation. Okay, so if we wanted to, we know the standard deviation, and somebody wants to ask you, give me an idea about what the minimum and maximum values are, this is how we would do it. Okay, if we know the range, we're kind of turning it around now, because the range comes from the maximum and minimum. If we have an idea about what the range is, we could estimate the standard deviation to be the range. Okay, you're away from your calculator, you're away from the computer, you got an idea about the range, but you want to estimate the standard deviation. Then this is how we could do that. And of course, this is an estimate. Okay? So for example, based on the data set 1 in Appendix B, males have a pulse rate, or have pulse rates with a mean of 67.3 beats per minute and a standard deviation of 10.3 beats per minute. Is it unusual for a male to have a pulse rate of 45 beats per minute? Okay. Now, when we think about this, I want you, as we start to move more into mechanical problems and away from kind of the conceptual things we talked about in Chapter 1 and some in Chapter 2, I want you to think about how you know the answer. Okay, don't just rush to the answer, but think about, how am I going to know this when I see it again? Okay? Everybody following me? Don't go on the momentum of, I'm in this section and that's what we're talking about and that's how I know what to do, because you won't have those kinds of clues on the test. All right, everybody following me? Okay, so, stepping back, we're looking at this. Is it unusual for a male to have a pulse rate of 45 beats per minute? Well, we just talked about this range rule of thumb, which gives us the range of typical values, the minimum or the maximum, right? So I could use the range rule of thumb to find out what's the minimum approximately and what's the maximum. And if this falls in there, then we'll say, yes, it's a typical value. If it falls outside of that, then we're going to say no. Okay? That's our strategy. So let's find out what the estimated minimum value is. X bar in this case, they said, was what? Okay, 67.3. And our standard deviation is 10.3. We do 67.3 minus 2 times 10.3. We turn our calculator on first, though. That helps. And I get 46.7. Okay. Which is that's enough for it. We don't even have to go any farther. Right? Because 45 falls below that. It's below the minimum. So we would say, is it unusual for a male to have a pulse rate of 45 beats per minute? We would say what? Yes. Okay, it's unusual. It's below it, so it would be okay. All right, questions about that? Right. So we need to know what the maximum to make sure it didn't go too far the other way. So just out of curiosity, we'd look at 67.3 plus 2 times 10.3. And so we get 87.9. So typical values for pulse rate for males fall between 46.7 and 87.9. Anything outside of that range, approximately speaking, we'd say is unusual. Okay? Yes?
You say that this is an estimate, though, with the 45 being so close to 46, could it still be?
Right, possible. I mean, in statistics and probability, which we'll talk about in the next chapter, I'm excited about that. But, you know, they don't predict the future. Okay? Really, it just kind of tells us what we see based on data. But when the next person comes in here, you know, they could be fine and their pulse rate may be in this range and it might not. Okay, so this really is an estimate. And like the name says, it's a rule of thumb. So there's certainly better rules, and we're going to look at some of them. Okay? All right, flipping it around and going the other way, here we have a data set, and these are the times required for an airplane to taxi out for takeoff. And I believe it's supposed to be in minutes. I was curious about this because I didn't know what their definition of taxi out was. I only got a little bit of the data, but I'd hate to think. Sometimes, I don't know. Anyway, just forget it. Here's the data, okay? What we want to do is estimate the standard deviation. And so we just said using the range rule of thumb, we can get an estimate for the standard deviation by looking at the range and dividing it by 4. Okay, because we're dividing by 4 because from the mean we went up 2 standard deviations and we went down 2 standard deviations. So that's 4 standard deviations in width altogether. Does that make sense? Okay, y'all are really quiet. Okay, so I'm going to look at my range. Looks like my largest value is largest? Okay, 37. And then the smallest looks like it's 12. Okay, we're going to divide that by 4. So 37 minus 12 is 25 over 4. That's about 6.25. Okay, 6.25. So an estimate of the standard deviation would be 6.25. Okay, it'd be interesting to know what the standard deviation was, but we won't take time to do that right now, just as a comparison. But this would be a good estimate. Okay? Questions about that? So 2 things I can ask you about the range rule of thumb, all right, in these 2 examples. Okay? Next rule, very important one, the empirical rule, or what is sometimes called the 68, 95, 99.7 rule, because those numbers are very important here. Okay? First of all, when we talk about the empirical rule, it only applies to data that's roughly bell-shaped, which you have a picture of that right here below the table. Okay? Or data that we might call what? When we were talking about the distributions, this looks like what kind of data? Normally distributed. Okay? Bell-shaped, mound-shaped, which is a pretty poor descriptor, but sometimes used, and normally distributed. Okay? Those are pretty much all the same. So it applies to that type of data. Okay? And it says approximately, I'm going to tell you the percentage of data that falls within so many standard deviations. Okay, we'll say within K standard deviations, blank percent. Okay, so within approximately 68% of our data lies within 1 standard deviation. Okay, of the mean. So that looks like X bar plus and minus 1S. Okay, if I look at the interval, plug in the mean and the standard deviation for those values, and compute that interval, then we would expect to have approximately 68% of our data. Okay? We have approximately 95% of our data that lies within 2 standard deviations. That's an interval of x bar plus or minus 2s. And finally, within 3 standard deviations of the mean, we have approximately 99.7% of our data. Okay? So you need to commit these numbers to memory. Within 1 standard deviation, we have about 68% of our data. Within 2, 95%. Within 3, 99.7%. Okay? Yes, all of this you should be familiar with. I would remember the numbers, and remember along with this that when we say that data is normally distributed or bell-shaped, that also implies that it's symmetric. We can fold it right along the middle, which is where the mean would be, also the mode and also the median, but we'll talk about that another day maybe. But if we folded this thing right in half along the mean, notice here's my interval from here to here is within 1 standard deviation. I went 1 standard deviation down, 1 standard deviation above. We said within that area we have 68%. Okay. All right, so we had 68% within the first standard deviation, but because of symmetry, that splits evenly into 34% above the mean, 34% below. Does everybody see that? Okay. All right, now I'm getting some nods. This is better. Okay, and then within 2 standard deviations, it says we have 95%. Well, they split the 95% in half, and then even subtracted from half of 95%, they subtracted 34% to say that, okay, this is the additional amount that we have in this little section. Okay, I don't expect you to remember all those numbers. I expect you more or less to remember the property, okay, and how you could get to the numbers. Half of 95 is what? 47.5? Okay, so from the mean to 2 standard deviations, we'd have 47.5% of our data. Or from the mean to minus 2 standard deviations, 47.5% of our data. So on. All right? So, got a couple of examples. It says, based on dataset 3 in Appendix B, body temperatures of healthy adults have a bell-shaped distribution. That's important. Okay, don't just read over the license to use the empirical rule. If we don't know that, then we can't use this rule. Okay, a bell-shaped distribution with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Okay, so I've got X bar is 98.2 degrees and S is 0.62 degrees. Okay, so using the empirical rule, which I intended not to type because I'm not going to say that on the test. Okay, you'll know to use the empirical rule because it says it's a bell-shaped distribution. Okay, so what is the approximate percentage of healthy adults with body temperatures between 96.34 degrees Fahrenheit and 100.06 degrees Fahrenheit? Okay, well, the first thing I need to know is how far those numbers are from the mean in terms of standard deviations. Okay, so one way we can do it is actually a little chart like the one we had up top there. Okay, the mean is going to be at the center, okay, because it balances the weight of the data. Okay, the mode, why is that at the center of normal data? It's the one that occurs the most, and with the data that we have here, this is the highest point, right? Why would this also be the median? Okay, center in what sense? No, with the median, we talk about it divides what equally? What about both sides? The number of values. Remember? I don't know if y'all looked at that. Make sure you go back. I don't think y'all looked at that video yet. But the median is at the center because it divides the number of values. Okay? We've got the same number of values above the median as we do below. So since this is symmetric, we would have the same number of values above as we do below. So here's a tip. For normally distributed data, the mean is equal to the median is equal to the mode. All right? For normally distributed data, the mean is equal to the median is equal to the mode. Okay? All right, so we got that at the... If I add and subtract 0.62, got 98.2 minus 0.62. Okay, when I subtract, I get 97.58. I'm going to go ahead and subtract again. Minus 0.62. 96.96, is that what you all got? Okay. 96.96. Okay, ideally, let's just scratch that out and call it 96.96. It'd be exactly the same. Okay? If I add 0.62 to the mean, we get 98.82. And if I add it again, I get 99.44. Let's call this that. Sorry. Okay. So what we would do is add and subtract until we get the numbers that we're interested in. Okay. These are the numbers that we're interested in. And how many standard deviations are they from the mean? 2. And so the empirical rule says within 2 standard deviations of the mean, we have approximately what? 95% of our data. Okay? All right? Questions about that? Okay? And then we could turn it around. Let's change to 68%. If we wanted to know what's the range of values that contains about 68% of our values, we'd look at how many standard deviations? 1. So we would look at x bar plus or minus 1s, or 98.2 plus or minus 0.62. Okay, 98.2 minus 0.62 is 97.58. And if we add 0.62, we get what? 98.82. We already had that on the chart. Okay, so within this range, we would expect to have about 68% of our data. Okay? Now, we're not going to get to talk about Chebyshev's theorem right now, but it does the same thing, just has a different formula. Okay, so look for that video after I do the class on tomorrow. Again about it on Tuesday. But yeah, I plan to be here. You have to go to the testing center, but it is on D2L. Yes. Okay. Alrighty. Chebychev's theorem. Let's see if we can talk about this. This is the same thing, except he had a different take on it than what we saw with the normal distribution or the empirical rule. First of all, this applies to any data set. Okay, it's not just limited to data that's normally distributed. Okay, any data set. So if we don't know anything about the distribution, if the question doesn't say anything about it at all, we're going to do Chebyshev's theorem. Okay? All right. So his rule says at least 1 minus 1 over k squared. Okay? At least. And these two words, they're really important. The last rule says approximately, but this one says at least. Okay? Not quite as, a little less accurate, let's say, because we don't know anything about the distribution. So at least this proportion or this fraction of data will lie within k standard deviations of the mean. And the intervals still work the same way. And I should note that k has to be greater than 1. Okay? So for instance, let's say is equal to 2. All right? Then we would say at least 1 minus 1 over 2 squared, which comes up to 3/4 or 75%. Okay, at least 75% of the data will fall between, don't let that scare you, x bar minus 2s to x bar plus 2s. We'll have at least 75% of our data in that range. Okay, if we're talking about within 3 standard deviations, that's 1 minus 1 over 3 squared. Okay, which gives me, it comes up to 8/9, because I've done this for many years now. I remember. So approximately 89, well, at least 89% of our data will fall within 3 standard deviations of the mean. Okay, so, you know, comparing that to what we had before we had 68, well, at 2 we had, what, 95, at 3 we had 99.7, okay? If you want to, you can remember these two numbers for Chebyshev's theorem. However, we could also, if we wanted to, talk about 2.6 standard deviations for Chebyshev's. Okay, it's not just limited to 1, 2, 3, but anything in for k as long as it's greater than 1. Okay, and when we do, if we put in 2.6, I would say 1 minus 1 over 2.6 squared. I get 0.852. So we'd say about 85%, at least 85%. Okay, at least 80% of our data is going to fall within 2.6 standard deviations of the mean. And that's just an example, you know, 2.6. So you see it does the same thing that the empirical rule does. It just has different numbers that goes with it. In fact, we get those numbers from this formula. Okay, so let's look at an example. According to the U.S. Census Bureau, the mean of the commute time to work for a resident of Boston, Massachusetts is 27.3 minutes. Assume that the standard deviation of the commute time is 8.1 minutes. Okay? What minimum percentage of commuters in Boston has a commute time within 2 standard deviations of the mean? Okay? Well, they're asking us to find what? The percentage, minimum percentage. So at least something, right? Do we know anything about the distribution of the data? Well, I mean, is it normally distributed? They don't tell us anything, but what they want to know is what percentage we expect to be within 2 standard deviations of the mean. And so because we don't know anything about the distribution, we're going to use Chebyshev's theorem. Okay, that's why we're using his theorem. And we already know he would say at least 1 minus 1 over 2 squared, which we said was 75%. at least 75% of the values will fall within 2 standard deviations of the mean. Okay? What minimum percentage of commuters in Boston has a commute time within 1.5 standard deviations of the mean? What would we do? Okay, so 1 minus 1 over 1.5 squared. Okay, still we don't know anything about the distribution, so Chebyshev's theorem is the best one to use. Okay, so we do 1 minus 1 over 1.5 squared. Okay, I get 0.55555555, or we might say at least 56%. Okay. All right, questions about that? Okay, in part C, it says, what is the minimum percentage of commuters who have commute times between 3 minutes and 51.6 minutes? Okay, well, I need to figure out what? How many standard deviations that is from the mean. Very good. So our mean was 27.3. And our standard deviation is 8.1. So if I keep adding 8.1 to that, we got 27.3 plus 8.1 is 35.4. It's 43.5. 51.6. Was that my number? Okay, so far we've gone up how many standard deviations? 3, right? This was the mean. So we've gone up 3. We're probably going to go down 3 too, but let's just check to be sure. 27.3 minus 8.1 would give me 19.2 minus 8.1. I got 11.1 and 3. Okay, so we were 3 standard deviations away from the mean. All right, the mean's right there in the middle. So we went 1, 2, 3 standard deviations from the mean. And so according to Chebychev's theorem, we would say what? 2 small words. At least 89%. Okay, very good. At least 89% of our data we would expect is going to fall between 3 minutes and 51.6 minutes. Okay? The people who, I saw a friend, she posted on Facebook this morning, it's nice to get up and get dressed for work and walk to your kitchen table. So she's in that less than 3 minute commute. She just has to go sit down at her table. That's what she does. I mean, she works. She just works from home. All right, very good. Okay, questions about that? Okay. Oh. Well. Okay. Make sure you're doing the homework on that so that if you have any questions about it, we can ask. I'm not quite done, though. Okay. Coefficient of variation. We got about 10 minutes. Coefficient of variation. We mentioned this earlier. The ball bearings from our ink pen and the tire tread, how many miles we could drive before we had to replace it. Okay, so the coefficient of variation, which is often denoted just VAR, coefficient of variation, is equal to the standard deviation divided by the mean. It just basically compares our standard deviation to a typical value in our data set. All right, and so that makes it possible for us to compare things from data sets that are very different. Okay, if we found the coefficient of variation for ball bearings and also found it for our tire tread or the miles before we had to replace it, then this would allow us to compare the 2 data sets. So how does that work? The senior class of a school district has a mean ACT score of 23 with a standard deviation of 4 and a mean SAT score of 1,100 with a standard deviation of 150. Which test has more variability? Well, looking at these, they're very different tests, right? What's the max score you can get on ACT? Like 24, 25? Something like that? Okay, SAT, depending on when you took it, 1,600. I think maybe it's up to 2,400 now. Is that right? There were 3 parts or something. Okay, they're very different. That's the point. Okay, so I'm going to do my coefficient of variation. I feel like this is not the right symbol, but we'll go with it for now. The standard deviation for the ACT was what? Okay, 4 over 23. Okay, that comes up to what? Okay, 0.1739. All right, and then for the SAT, we've got 150 over 1,100, which comes up to what? 0.1363. Okay. Okay, if we round to 4, okay. All right, so which one of these seems to be more consistent? It would be the SAT because it's smaller. The coefficient of variation, the question was which test has more variability? And if we're answering that question, it would be what? ACT. The ACT has more variability. All right? Because its standard deviation compared to the mean is larger than the standard deviation of the SAT compared to its mean. Okay. All right. This might appeal to most of you. Suppose where'd it go? Suppose the systolic blood pressure of a random sample of 100 students before exercising has a sample mean of 121 with a standard deviation of 14.1. The systolic blood pressure after exercising is 135.9 with a standard deviation of 18.1. Is there more variability in systolic blood pressure before or after exercise? Okay, so before exercise, we would do what? Okay, 14.1 divided by 121.1165. Very good. And then after, we had what? 18.1 divided by 135.9. We get what? 1.1332. Okay, so which one, what's the question? Is there more variability before exercise or after? We'd say what? After, because after is larger. Okay, after is larger. There's more variability after. Okay, all right, very good. Questions about that?